Hello everyone. So today we are going to start another unit of our core course on classical mechanics and classical electromagnetism. So this unit starts with the classical electromagnetism, and in order to start our study we will first review the Maxwell's equations, and then we will move towards the more interesting and advanced stuff. So let me begin by where we had left in the BSc second year. Remember, we had these four different laws in case of the steady state field equation, that is where we could assume that the net charge density or the current density is always the same. Okay, so in that case, the Gauss's law takes is written like this. So del dot E, the divergence of E is 4 pi rho. That we already know. Okay, that if rho is the charge density, we will have the divergence of E should be equal to 4 pi rho. Then the other thing is that because the electric field is conservative in nature, electric force essentially are conservative in nature. So therefore, the electric field should be irrotational, and that means curl of E should be 0. Similarly, the analog of the Gauss's law in case of magnetism should be written as divergence of B is equal to 0. And similarly, we could write del cross E, del cross B, that should be equal to 4 pi by C J. So this is actually the Ampere's law, and according to this, the magnetic field works normal to the direction of the propagation of the charges or the current. Now, once we consider, so these are actually the free field equations. Now, if we work in the medium, then we need to replace E by D, and which is called actually the displacement vector, and B by H, and then these four equations will modify to del dot D, that should be equal to 4 pi rho, del cross E, that will still be okay, that should be 0, del dot B should be equal to 0, and del cross H, that should be equal to 4 pi by C and J. In fact, so this is the equations. So now with H and H is given, with B is given, E is given as, in fact, with D being equal to the epsilon times E, and H is going to be B by mu. So these are the things. So in these equations, if we take the curl of this equation number, so let's give some numbers to these equations. So these are equation number 1, these are equation 2. So if we just take the curl of the last four, taking curl on the fourth 2.4, curl of 2.4, what we will get? This should be divergence, taking divergence, so that would be del dot del cross H, so that's going to be 4 pi C del dot J, and that means, now this is what? Here we have two identical vectors, so this is going to be a scalar, zero scalar product, so that means that, so this is 0, and this implies the del dot J is 0, and that means this is a steady state flow of the currents. So this holds good so far. Now, what is J? there is another law that in conductors, according to Ohm, J is essentially proportional to E, or J is given as sigma times E, where sigma is called the conductivity of the medium and E is the electric field. So, using these relations, we should be able to perfectly work with the whole electromagnetism. However, when we think about so this is the case when we are talking about the electrostatic and the magnetostatic forces. However, the situation is not this is not the correct situation. We know that the flow of charges might cause the loss in the density of the charges in certain media. Okay, so that means we should be making the rho and j to be the time dependent, and therefore the Maxwell's equation should also get modified in this slide. So let's first check what happens what went wrong when we consider the dynamic case. That is, so let me write the dynamic electromagnetism. So this is what we will discuss now onwards. Magnetism. So what we are doing now, rho is now a function of time. What does it mean? Now this means the current will flow. So for example, if J is the density, so imagine if we have certain area and this is the normal direction, this is the J vector. So then the current flowing outwards from this area, say ds, so that would be simply j dot ds. That should be the whole thing. So this is going to be j dot n hat ds. Now this current should be essentially the loss in the charges. The rate of loss of charges into the media, that should be given by the outward flow of the current. So now this is minus dq by dt, and let me write these values. So this is going to be d by dt, and what is q? Q is nothing but the charge density times the volume. Okay, so that means, so because that is the only function of time, so therefore we could also write this as minus d rho by dt times d. So this should be, this integration is taken over the whole loop. So now we have these two equations. So let me just apply the Gauss's law over here, Gauss's theorem. So using Gauss's theorem, we know that we could write this as del dot j dot n hat ds is going to be divergence of j dv, and then we also have this thing. So this is minus d rho by dt dv. So this immediately implies that the del d rho by dt, if we take d rho by dt on this side and del dot j, so this should be equal to 0, and that immediately tells that this whole thing should be 0. So this means d rho by dt plus del dot j, this should be equal to 0. So this is our equation of continuity of the flow of charges. So what it suggests, that the Rho and J are two dependent quantities. So that means there should be a relation between E and B when the charges flows. That is the case of dynamic electromagnetism. So this is an early hint of the unification of the electric force and the magnetic force. So with this direction, Faraday had done an interesting observation. What he did was the following. So in other than this, in fact, there was an observation by Faraday. So this is equation number 3. So Faraday's observation. So what is Faraday's observation? So this is the EMF is induced when the rate of change of flux, the rate of magnetic flux change gives rise to an EMF. So that means, so this is E dot dl, and here we have minus d by dt B dot ds. Now, if we apply the Stokes law, we could write this as del cross E ds is equal to minus d by dt minus, once again, this is the only time varying thing, so this is going to be del because we have this to be dependent upon the other things as well. So if we just put these things inside, and because the area is non-zero, therefore, so this will imply that del cross E, in fact, there should be a factor of 1 over C as well, because we are working in the Gaussian units. So del cross E plus del B by del T should be 0. So this is the Faraday's law. So this also hints for these things. Now, if we want, now remember earlier we had del dot J is equal to 0 when we were discussing the static electromagnetism. So this means we need to modify our relations so that the equation of continuity is followed. So this observation of Faraday gave an idea about how the modification should be done. So what was the suggestion? The suggestion was to introduce what is known as the displacement current, and that means the suggestion, so because E is essentially modifying the B and B is related with the J through the curl of B, so therefore that means the J itself should be modified in order to take into account these changes, and that is done by this relation. So J is replaced by J plus del D by del T. So with this D, as we already know, is essentially our displacement vector. So with these sorts of modifications, we need to rewrite our Maxwell's equations, and we could again check that we can indeed get the equation of continuity right for the case of dynamic electromagnetism. So let me do it one by one. So remember, with these things, we will not reach this particular relation, the first, the Gauss's law, that's not going to receive any correction at all. However, the second relation, which is the curl of E, that's anyway modified according to the Faraday, which will be the correct thing to say. And then we will have the third relation. This is going to be divergence of B is 0. That's not modified at all. However, the fourth one, which is del cross H. So that was 4 by C and J, but now J has modified to 1 over 4 pi del d by del t, and therefore this relation will become del cross h minus 4 pi will cancel. We will have 1 over c del d by del t is equal to 4 pi by c and j. So now we have these four Maxwell's equations which are in the correct form. So in order to study the dynamic electromagnetism, we should start from these four equations. And of course, we had J is equal to sigma E. I would write this also as another equation, say 4.5 for my own preferences, because it looks like that we need to use this again and again, and maybe together with these things it would be worthwhile to write d is epsilon e and h is equal to b by mu. Remember what epsilon and mu's are. So epsilon is the as you know, magnetic susceptibility, mu is the magnetic susceptibility of the medium, and epsilon is the permittivity of the medium. So epsilon and mu are going to be unity for the space. Okay. So you could check that when these are 1, we will get the equation for the free space, which will again be written in terms of E's only. That is, there is going to be no B, D and H. Now let's again make sure, in order to make sure that this change in J is working, let us again take the divergence of the equation number 4.4 to make sure that we indeed get the equation of continuity. So taking divergence of 4.4, what we will get? Once again, this is going to be the scalar product of the curl of H minus 1 over C del t. Now d is going to be del dot d, because we already know that whether we do take the derivative first with respect to time or first with respect, or we take the divergence, the results are going to remain unchanged. That's the beauty of the partial derivatives. So this is going to be equal to 4 pi by c, and we will have del dot j. So this is obviously going to be 0. Del dot t, that is going to be 4 pi rho. So this is going to be 4 pi rho upon c. Then we have 4 pi upon c. So that means we will have del rho by del t is equal to del dot j. So let me again write and rewrite this equation. So we will have minus 4 pi by c del rho by del t, that should be equal to 4 pi by c del dot j, and therefore by cancelling these things we realize that we again obtain the same equation of continuity, which was equation 3. So this means this whole setup is working fine. So from here onwards, we will be working with these equations. However, let us start studying some more interesting features of this equation of continuity. So now what I will do, I will basically be using the relation 4.5 where J is sigma e. So using J is equal to sigma e in 3. Let us see what happens. So we will have del rho by del t, and then we will have del and then dot e, because sigma is a constant. So this is 0, or what we will write in next step, del rho by del t and del dot e. So that's going to be, E is basically d over epsilon, and now this is 4 pi rho. using our first Maxwell's equation. So this is going to be 4 pi rho sigma upon epsilon rho to be equal to 0. Now, if we just do the dimensional analysis, here we have rho and here we have time. So here we have rho, so that means in the denominator we should have something which fixes, which is of dimension time. So I will just write this as 1 over tau and rho, that should be equal to 0. So the solution, so this will imply that the solution is going to be e to the power minus t by tau with, what is tau? Tau is defined as epsilon by 4 pi sigma, and this is called tau r, or the relaxation time. So this is the equation number 5. So tau is known as the relaxation time. So tau is the relaxation time. So this represents, so this is essentially a measure of how fast a conductor releases the charges. So as we could see, so sigma for conductor is greater than sigma for semiconductors, and then sigma for insulator, and that immediately tells tau is going to be, basically this is the thing, and therefore we see that the tau for conductor is much smaller than the tau for semiconductors and then the tau for insulators. So in order to give some idea how far these numbers vary. For example, tau for copper, so this is about 10 to the power minus 22 for copper. This is about 10 to the power, so this is second, minus 8 seconds for the silicon, and this is about 10 to the power 4 seconds for the quartz. So clearly you could see that conductors could release, because the conductors could release the charges at a much shorter time compared to the semiconductor or the insulators, and therefore they are the good source of the current, the good sources of the good source of flowing the electricity. Okay, so that is one thing. Another thing is that in this relation for tau, the epsilon, which is the permittivity, is sitting in the numerator, and that means if we could raise epsilon, that means we could retain the charges for longer period even in a given conductor, and that is exactly what this dielectric material does. We essentially try to have materials with larger epsilon to retain the charges inside a conductor. Okay, so this is all about the relaxation time. Let me quickly talk about another thing. That's another time, and that would also be very useful, and this is known as the diffusion time. So in order to find the diffusion time, let me try to estimate the diffusion, estimation of diffusion time. So this will be represented by tau d, as you will see shortly. Okay, so let me first define what diffusion time is. Diffusion time is the time in which charges start diffusing to a conductor, to a material or a medium. Okay, so in order to calculate the diffusion time, let me start taking the equation, the Faraday's law, taking curl of, so we could either take curl of the Faraday's law of the equation 4.2. So we could either take the curl of 4.2 or we could take the curl of 4.4. So that would give you del cross E plus we had 1 over C del V by del T. So this is del by del T of del cross. So this should be 0. Now this is minus del 2 of E and then gradient of del of E. So this is the gradient of E. And that should be equal to 1 over C del T, and del cross B is how much? Del cross B is 1 over C 4 pi by Cj minus 1 over C del D by del T. So this is what we know. Well, this is I think 4 pi by Cj plus 1 over C del D del T. So with these things, the equation that we will get is the following. We will use D is equal to epsilon E and we will use J is equal to sigma E. Okay, so this is sigma E, D is epsilon, that is what will be used. So if you do that, we will get del 2E and del dot D is equal to how much? That's going to be 4 pi rho upon epsilon. So this is going to be 4 pi upon epsilon, and then we will have gradient of rho plus we will have 1 over C del T 4 pi by C J is sigma E. So this is going to be 4 pi by C square, and then we have sigma, and this is going to be del E by del T, plus we will have the higher order term, basically that would be del 2 by del T2. I will just ignore that. So this is the thing that we were interested in, okay? Or in the other, or if we just write the simplest form, so this is written as 4 pi by sigma upon C square, and then we have del E by del T, that should be equal to, approximately equal, because we had ignored this term. Okay, so this is ignored because this is second order term in the derivative of T. Okay, so this is del 2E, we have 4 pi by epsilon del rho, so that will be 4 pi by epsilon gradient of rho. So now this is basically, as we would realize, is essentially the diffusion equation for D. Now, what is the gradient? The gradient is del over del R type of things. Okay, so that means we could take del 2 to be like 1 over L square, where L is essentially the size of the wire, okay, or thickness. Then the del over del T, we would interpret this as 1 over tau D. So if we do that, what we roughly get is the following. So we could cancel these E's and E's. We will have 1 over L square is roughly equal to 4 pi sigma by C square 1 over tau D, and from here what we get is the following. The tau D is going to be roughly equal to 4 pi sigma upon C square L square. So if we take L to be unities, L is equal to about 1 millimeter, that is the typical thickness of a wire, what we realize that tau D for a given medium is going to be much larger than the tau relaxation. So that is an interesting observation. What it says that for example, tau d is going to be tau for, say for example, a conductor. Okay, so the charges diffuse at a much later time than they are actually released. So that gives an idea why the conductors could flow the electricity. Okay, so that is all for now. From next time onwards, we will be discussing about the wave equations that will come from the Maxwell's equations and many more interesting stuff. However, those things would all still be related to the review of what we had already studied. And once that is completed, we will move forward to study the new things related to this. Thank you.